All right, let's talk about polarization. So last week we discussed how electromagnetic waves, also known as light, have an electric field and a magnetic field as part of them. And we didn't really discuss how that works, and today we probably won't really get into the details of how the electric field and the magnetic field interact, but what's going to be important is sort of the directions that they move in. More specifically, the direction that the electric field moves in. We're going to kind of forget about the magnetic field for today. So let's say I've got light traveling in this direction, okay? That's the direction my light is shining. What direction is the electric field going in? Now this may seem unrelated, but this is actually important for today. The electric field can oscillate up and down in any direction perpendicular to the way that the light is traveling. So one way my electric field could oscillate is like this, up and down like that. So my electric field is oscillating up and down while my light is moving this direction. Notice that the direction of motion of the light is perpendicular to the direction that the electric field is oscillating. Now, this sort of looks like the electric field is oscillating in this direction, but we say up and down because really what's happening is as the light travels this way, say, I had it going this way before, but imagine it's going this way, your electric field is going up and down, etc. Okay, so what other ways could the electric field be oscillating? And usually we draw the electric field direction like this. So this is our E field direction. Okay, what other ways could this be oscillating? Well, let's imagine there is a laser behind my whiteboard that's shooting a light directly at the camera. Now, this case that I've drawn here, the electric field's oscillating up and down, would look like this. So the electric field is going up and down, pointing towards the camera like I did with my little demonstration here. So now maybe it's more obvious what other directions the electric field could point in. It could be like this. It could be like this. It could be like this. And really it could be anything in between all of these four. So any line I could draw on the board that passes through this point, that is a direction the electric field could oscillate in. Okay, why is this important? The direction that the electric field is oscillating in is called the polarization of the light. So let me back this down to just my single line here. So if I see a light ray coming towards me, remember it's coming out of the board like this, and the electric field is going up and down like that, we say that this is linearly polarized, and then we would say in this direction. So this is linearly polarized light, which means that the electric field is oscillating in one direction only. There's another type of polarization called circular polarization, which is where the direction of the electric field actually rotates around as it moves, but that one's a little bit more complicated. We're not going to get into that for this week's lab. We're only considering linear polarization, which is where electric field is oscillating in one direction, namely up and down here. Okay, so what can we do with this? Well, there's a thing called actually before we get into polarizing filters, let me point out one more thing, is that this is an individual ray of light, or an individual light wave. Light that we interact with on the day-to-day basis is really a collection of tons and tons of light waves. Now, let's say that my source is sending me a bunch of light waves and they're all polarized the same direction. So there's a bunch of light waves, all with polarizations like this. You get the idea here. Polarized up and down. That's what we call polarized light, where every beam, every wave of light in the packet of light that's coming towards you is polarized in the same direction. Contrast that with natural light, or unpolarized light. That's where light is coming in at every different polarization angle you can think of. So remember, each individual beam has its own polarization, but we usually consider the polarization to be a group trait. So right here, this is unpolarized light. This is light that has light waves of each different polarization versus polarized light, which is where they all line up. Okay, so let's talk about polarizing filters. These are often called polarizers or polarizing lenses. I tend to say polarizing filters a lot, but just know that those all mean the same thing. Okay, I've drawn these lines in because every polarizing lens has a direction of polarization. Namely, the direction of polarization here is up and down. Now you can think of this almost as a physical grate. This is not really how it works, but it's a good analogy. And so when light comes in that is polarized vertically like this, up and down, it can pass through these slits easily, and you get all the light back out the other side, continuing along. Okay, but what if it's not lined up? Let's say I've got light coming in, or actually, we'll do it this way. So I'm going to keep my light vertical. I'm going to rotate my lens so that it is now polarized like this. So all I did was just take it, rotate it 90 degrees. Now you can see that the polarization of the light doesn't match up with the polarization direction of the lens, and actually 100% of this light gets blocked out. You get no light over here. Nothing comes out. Okay, what about in between? So let's handle the case where it's in between. You might think that, based on the way I've described it so far, if the angle doesn't line up exactly, you won't get any light through at all, but that's actually not true. What we find is that if the angle of the polarizing lens is not 90 degrees to this, but just some other angle in between 0 and 90, we do get light out the other side, which has become polarized in the direction of the polarizing lens, but the intensity is less, so less intensity. And intensity is synonymous with brightness here. So you get less bright light out the other side, and it's been polarized in the direction of this filter. Okay, now the equation that governs this is called Malice's law. Okay, so Malice's law says that, and to set it up, let's imagine we send in just natural light polarized in any direction, like this. So this is natural light, sending it through, first I'm going to send it through this polarizer, where I set it up vertically, so now the only thing I get out is vertical light. Then I'm going to send it into another one, and this one is going to be at some angle. All right, so the angle of the polarization direction is right here, so we're going to call that phi. All right, and that's just the angle from the vertical, which is basically from the polarization of the light coming in, which is why we needed to send it through a polarizing filter first to sort of make sense of it. The light I get out the other side is going to look like this because it matches up with the direction, but what's the intensity? So if the intensity right here was I0, then the intensity I get out over here is I0 times cosine squared of the angle. Now the first thing to note is that cosine of 90 degrees is 0. So if I turn this to 90 degrees, we get no light back out, which makes sense with what we learned from before. And if cosine of 0 is basically 1, so 1 squared, we get the same amount of intensity out. So if these were lined up perfectly, you get the exact same amount of intensity you had here over here. And this is called Malice's law, and the general form is written like this. The intensity on the other side of the polarizer is equal to the intensity coming into the polarizer times cosine squared of the angle of the polarizer. Okay, so we're going to use this today just briefly at the end, but before that we're going to explore some applications of polarization and basically how it works.